US Physics Olympiad, year 2014, USA PHO exam. For whole contest that were given 6 problems, Part A 4 problems, 90 minutes, and Part B, after a break, another 90 minutes for 2 problems. All solutions for all 6 problems you can find below this video in the reference of the description. Problem A1. A unicyclist of total height h goes around circular track of radius r while leaning inward at an angle theta to the vertical. The acceleration due to gravity is g. Question A. Suppose that h much less than r. What angular velocity omega must the unicyclist sustain? Question B. Now model the unicyclist as a uniform rod of length h, where h is less than r, but not neglectable. This refined model introduces a correction to the previous result. What is the new expression for the angular velocity omega? Assume that the rod remains in the plane formed by the vertical and the radial directions, and that r is measured from the center of the circle to the point of contact at the ground. Solution for question A. Here is the picture. We have a unicyclist in form of this red line, which is moving in a circle radius r. If we choose a frame of reference which is rotating around this axis with the angular speed omega, in this frame our unicyclist is stationary. We just need to solve a static problem. For static problem we need to equalize all horizontal and all vertical forces and equalize total torque to 0 around any axis. Let's do this. We have 4 forces acting on this unicyclist and this frame of reference. One force is a force of friction F, other force is a normal force N. Also we have a force of gravity mg applying to the center of this rod, and also we have fictitious centrifugal force mr omega square in this rotational frame of reference. As we can see, force of friction must be equal to this mr omega square. To equalize horizontal force, normal force must be equal to mg, and also we have torque around point of contact. We have counterclockwise torque from force of gravity and clockwise torque from this centrifugal force. Let's write this equation. It will be this one. On the left we have a torque from force of gravity, and on the right we have torque from this centrifugal force. Here we use knowledge that h much less than r. From this equation we can find that omega equal square root from g over r multiplied by tangent theta. That's the answer for question A. Let's do question B. Now, because we cannot neglect by height h of this unicyclist, we have to split him on little masses dm, and to count what is total torque we need to do integral. Now total torque created by centrifugal force will be this one. Integral from r omega square z dm, where r is distance of this element dm from center of rotation, omega is angular velocity, z it's the height of this element above the ground, and dm it's a mass. Now we have to express our variables in this equation through variable which is distance from point of contact to our element dm. So from this point we have dm equal mass over total height multiplied by ds, z equal s cosine theta, that's a height, and r equal big R minus s sine theta, and the limits are from 0 to h. Using this variable s, we can express our torque by this integral. So finally this torque equal to this expression. And now we need to equalize it to torque created by force of gravity. Torque from force of gravity equal this expression, and now we can equalize them and find what is omega. And omega equal this expression. That's a solution for question B. US Physics Olympiad, year 2014, USA, PHO. Final exam. Problem A2. A room air conditioner is modeled as a heat engine run in reverse. An amount of heat QL is absorbed from the room at a temperature TL into cooling coils containing a working gas. This gas is compressed adiabatically to a temperature TH. The gas is compressed isothermally in a coil outside the house, giving off an amount of heat QH. The gas expands adiabatically back to a temperature TL, and the cycle repeats. An amount of energy W is input into the system every cycle through an electric pump. This model describes the air conditioner with the best possible efficiency. Assume that the outside air temperature is TH and the inside air temperature is TL. The air conditioner unit consumes electric power P. Assume that the air is sufficiently dry so that no condensation of water occurs in the cooling coils of the air conditioner. Water boils at 373 kelvins and freezes at 273 kelvins at normal atmospheric pressure. Question A. Derive an expression for the maximum rate at which heat is removed from the room in terms of the air temperatures TH, TL, and the power consumed by the air conditioner P. Your derivation must refer to the entropy changes that occur in a Carnot cycle in order to receive full marks for this part. Solution. As we see from the description, this cycle consists of two adiabatic and two isothermal processes. During adiabatic processes, the heat is not transferred. It means that full entropy change is zero. And also during whole cycle change of entropy is zero, because this is a Carnot cycle, and we can write by definition what is the change of entropy. Change of entropy ds equal dq over T. In our case, we have two adiabatic processes where dq is zero, and we have two isothermal processes with a constant temperature. And because total change of entropy is zero, we have this equation. We have Q high over temperature high equal Q low over temperature low. Also we have energy conservation. We have Q high equal Q low plus work done over the system W. From these two equations we can eliminate Q high and we will get Q low equal W multiplied by T low over T high minus T low. And this is all what we need. Now we just need to divide this Q low over temperature to get the rate with which this heat is removed from the room. This will be QL over time T, which is equal power multiplied by this coefficient. This is the answer for question A. Question B. The room is insulated, but heat still passed into the room at a rate R equal K delta T, where delta T is the temperature difference between the inside and the outside of the room, and K is a constant. Find the coldest possible temperature of the room in terms of TH, K, and P. Solution. We already found that K dt, the rate with which the heat is removed, that's equal QL over T, which we found in the previous question. That was P multiplied by TL over TH minus TL. But denominator, that's dt in our terms. And the TL we can express through TH minus dt. So from here we can do quadratic equation. So for this equation we have a solution in this form, and only positive root has a physical sense. So we can find what delta T, and after that find what is lowest possible temperature. That will be this expression. That's the answer for question B. Question C. A typical room has a value of K equal 173 Watt per degree Celsius. If the outside temperature is 40 degrees Celsius, what minimum power should the air conditioner have to get the inside temperature down to 25 degrees Celsius? Solution. From this quadratic equation we can find what is this power. That will be this expression. Now let's put numbers. So in our case delta T equal 15 degrees and the lowest temperature equal to 25 degrees plus 273 to convert Celsius to Kelvins. And totally a result will be 130 Watt. That's the answer for question C. US Physics Olympiad, year 2014, USAPHO. Final exam. Problem 8.3. When studying problems in special relativity, it is often the invariant distance ds between two events that is most important, where ds is defined by this equation, where c equal 3 by 10 power 8 meters per second is the speed of light. Question A. Consider the motion of a projectile launched with the initial speed v0 at angle of theta 0 above the horizontal. Assume that g, the acceleration of free fall, is constant for the motion of the projectile. First, derive an expression for the invariant distance of the projectile is a function of time t as measured from the lunch, assuming that it is launched at time t equals 0. Express your answer as a function of any or all of theta 0, v0, c, g, and t. Question 2. The radius of curvature of an object's trajectory can be estimated by assuming that the trajectory is a part of a circle. Determine the distance between the end points and measuring the maximum height above the straight line that connects the endpoints. Assuming that we mean invariant distance as defined above, find the radius of curvature of the projectile's trajectory as a function of any or all of theta 0, v0, c, g. Assume that the projectile lands at the same level from which it was launched, and assume that the motion is not relativistic, so v0 much less than c, and you can neglect terms with v over c compared to terms without. Solution. In our case, we have for delta t equal t, delta x equal v0 cosine theta 0 t, dy equal v0 sine theta 0 t minus 1/2 g t square. When we put these meanings to our expression for events, we have s square equal this one, or after simplification, this one. That's the answer for question I. Solution for question 2. In time-space frame of reference, we have for v much less than the speed of light, invariant distance approximately equal this expression. And we can find what is total time by using this equation. So it means that invariant distance for time t will be this one. And now we can find what is the height in this time space. That's a z. Maximum height will be this expression. And now we can find what is approximate curvature of this curve. Suppose that this is the graph of our trajectory in time-space coordinates s and z. In that case, AB will be distance this one, and z, that's a height this one. And now we can find what is the radius of this curve. We can find it from such equations. We have s approximately equal radius multiplied by small angle theta, where theta is not theta 0. That's a different one. And also we can find what is z. So we have maximum height approximately equal this expression, which is r theta square over 8. And now from these two expressions we can eliminate theta, and from here we can find what the radius is approximately this one, or c square over g. That's the answer for question 2. Part B. A rocket ship far from any gravitational mass is accelerating in the positive x direction at a constant rate g, as measured by someone inside the ship. Spaceman Fred, at the right end of the rocket, aims a laser pointer toward an alien at the left end of the rocket. The two are separated by a distance d, such that dg much less than c square. You can safely ignore terms of the form of this one. First question. Sketch a graph of the motion of both Fred and the alien on the space-time diagram provided in the answer sheet. The graph is not meant to be drawn to scale. Note that the t and x are reversed from a traditional graph. Assume that the rocket has velocity v equals 0 at time t0 and is located at position x equals 0. Clearly indicate any asymptotes and slopes of the asymptotes. Second question. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. Solution. Here we have a graph ct as a function of x, and because spaceship is moving with acceleration g, in regular case we have on axis y ct is linear to time, and on graph x is quadratic to time. So it means that in regular case we have to make a reverse parabola. But because speed cannot exceed speed of light, we have slope of each curve must go to this asymptote, and finally got very close to it. And the question is, what is the distance between alien and Fred finally? Because in moving frame of reference the distance became shorter. It means that these two curves, they have same asymptote, which has slope c, speed of light. And both trajectories looks like some kind of hyperbola. Basically, this is the answer for question 1. Question 2. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. Solution. Let's draw the picture for this process. To solve this problem, we replace the light with a series of discrete flashes. Then find how the frequencies of these flashes are seen by Fred and the alien. Let Fred emit a flash of light at time t0 and the second flash of light at time t equal tau, where tau is very small. Let the alien see the flashes at time t1 and t2, which we showing on this diagram. Then by ordinary kinematic we can write equations. For the first flash we have for time t1 this equation. So it means that distance d was reduced by 1/2 gt1 square, and that's equal to c multiplied by t1. Here we have a distance covered by flash of light for time t2 minus tau. That's equal to position of Fred after time tau, which is 1/2 g tau square plus d, minus position of alien at point t2, which is 1/2 g t2 square. So we have these two equations, and let's subtract from second equation first equation. So after that we have this equation, and now let's delta t be t2 minus t1. We have this equation, and because g tau over 2c it's very small, this approximately equal tau. And because g is very small, and we are looking only for the first order of G, we can say that T2 approximately equal T1 approximately equal D over C. And finally we have F-island over F-fret equal tau over delta T, or approximately it's 1 plus GD over C square. That's the answer for question 2 in part B. US Physics Olympiad, year 2014, USAPHO. Final round. Problem A4. A positive point charge Q is located inside a neutral hollow spherical conducting shell. The shell has inner radius A and outer radius B. A is not neglectable. The shell is centered on the origin. Part A. Assume that the point charge Q is located at the origin in the very center of the shell. First question. Determine the magnitude of the electric field outside the conducting shell at x equal B. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equal A. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Part B. Assume that the point charge Q is now located on the x-axis at the point x equal 2A over 3. Question 1. Determine the magnitude of the electric field outside the conducting shell at x equal B. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equal A. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Question 5. Sketch a figure showing the electric field lines, if any, inside, within and outside the conducting shell on the answer sheet provided. You should show at least 8 field lines in any distinct region that has a non-zero field. Solutions. First, let's do the picture for part A. We have charge Q in the center of this sphere, and we have a spherical shell with inner radius A and outer radius B. First question. Determine the magnitude of the electric field outside the conducting shell at x equal B. Solution. Here we can use a Gauss law, and according to this Gauss law and due to symmetry, if we have inside of a spherical region charge Q, the outside electric field will be this expression as a function of R. It means that on the distance B, just outside the shell, electric field will be this one, 1 over 4 pi epsilon 0 Q over B square. That's the answer for question 1. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Solution. Because the shell is conductor, we have a zero electric field inside of it, because electric charge distributed on the inner shell with a charge negative Q, and there is a charge positive Q on the outside side of the shell, and both charges are uniformly distributed. It means that inside of this shell electric field is zero due to Gauss, and due to Gauss inside the shell with distance less than a, electric field is the same as outside the shell, and we can sketch the graph. And finally we have this expression for electric field for question 2, and let's sketch it. Here we have a graph for this behavior where we have two parabolas from right side and symmetrical from left side with a 0 between negative b and negative a, and the positive a and the positive b. That's the answer for question 2. Question 3. Determine the electric potential at x equal a. Solution. Because this shell is conducting, it's an equipotential surface. It means that the potential in point A equal to potential in point B. Outside of this radius greater than B, electric potential the same as potential for charge inside the sphere. So it means that this is the expression for potential in point A and B, which is equal 1 over 4 pi epsilon 0 q over b. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Solution. So we have potential outside of this shell for x greater than b equal this one. For x between a and b, that's a constant, same as in point b. And for x less than a, that will be same as for point charge, but shifted by this constant, negative 1 over a plus 1 over b. If we sketch this, that will be like this. X greater than b, we have regular potential for point charge. Here between a and b, that's constant, and less than a, that will be shifted by constant. So that's the answer for question 4. Part B. Assume that the point charge Q is now located on the x-axis at point x equal 2a over 3. Question 1. Determine the magnitude of the electric field outside the conducting shell at x equal b. Solution. Now, because inside the shell electric field still 0, it means that we have a negative charge Q distributed on inner surface, but now it's distributed not uniformly. It's distributed exactly like the way to cancel charge in point 2a over 3, which is not symmetrical. And after that, the charge on outside surface will be distributed uniformly due to same Gauss, and we have the same answer as for part A, question 1. So that will be the answer for question 1. Electric field in point B equal 1 over 4 pi epsilon 0 q over b square. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Solution. So for the field outside the shell for x greater than b, we have the same result as for point charge in the center of the sphere. But inside the shell between a and b, we have 0 electric field, and for x less than a, we have more complicated situation, because it depends on the distribution of charge on the inner surface, and that is required is that it diverges at x equal 2a over 3 and is higher at x equal a than at x equal negative a. So basically one can find the field for r less than a exactly using the method of image charges. For r less than a, the shielding charges on the inner surface produce the exact same field as a single point charge would. The locator of this image charge can be found by inverting the original point charge about the circle r equal a. But this is out of the scope of this problem. So finally we can sketch the graph for this electric field that will look like this. So we have for x greater than b from right side and symmetrically from left side we have the same field as for point charge in the center of the sphere. After that we have zero field between a and b from both sides, and inside the shell for x less than a we have diverging for x equal to a over 3 and kind of complicated field, but still back proportional to 1 over r square, where now r is distance to point to a over 3. So that's the solution. Question 3. Determine the electric potential at x equal a. Again we have electric potential outside the sphere for x greater than b, the same as for point charge in the center of this sphere. So that will be this expression. Potential in point A the same as potential in point B, because this shell is equipotential surface. So that's the answer for question 3. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. So here we have the same situation. Outside of this shell for x greater than b we have the same potential as for the point charge, and between a and b we have constant potential, and after that we have potential back proportional to 1 over r, where r is distance to point x equal to a over 3. So that's the main idea. And the graph for this potential will look like this. That's the same as for point charge in the center of this sphere outside B, and it's a constant between A and B, and it looks like 1 over R inside this shell for x less than A. Question 5. Sketch a figure showing the electric field lines, if any, inside, within and outside the conducting shell on the answer sheet provided. You should show at least 8 field lines in distinct region that has non-zero field. So obviously electric field will be spherically symmetrical outside the shell when r greater than b, must be 0 inside the shell between a and b, and the field lines must be terminated perpendicular to the surface of conductor. That's the picture for this electric field lines, and this is the answer for question 5. US Physics Olympiad year 2014, USAPHO. Final round. Problem B1. A block of mass big M has a hole drilled through it so that a ball of mass small m can either horizontally and then pass through the block and exit vertically upward. The ball and block are located on a frictionless surface. The block is originally at rest. Question A. Consider the scenario where the ball is traveling horizontally with a speed v0. The ball enters the block and is ejected out the top of the block. Assume there are no frictional losses as the ball passes through the block, and the ball rises to a height much higher than the dimensions of the block. The ball then returns to the level of the block, where it enters the top hole and then is ejected from the side hole. Determine the time t for the ball to return to the position where the original collision occurs, in terms of the mass ratio beta equal big M over small m, speed v0, and acceleration of free fall g. Question B. Now consider friction. The ball has a moment of inertia I equal 2 over 5 mr square and is originally not rotating. When it enters the hole in the block, it rubs against the surface so that when it is ejected upwards, the ball is rolling without slipping. To what height does the ball rise above the block? Solution. Question A. First, we have to emphasize that here we have horizontal momentum conservation and energy conservation. It means that we can find what is the speed of block and ball in the moment when the ball is start to fly. That will be momentum conservation. M small plus M big multiplied by Vx, where Vx is a common horizontal speed. That's equal initial momentum, which is M small multiplied by V0. And from here we can find what is Vx. This is this expression. And now we can find, using energy conservation, what is the initial vertical velocity of the ball. From this energy conservation we can find what is Vy square. That will be this expression, V0 square multiplied by big M over small m plus big M. And now we can find what is time to fly for block. That will be T1 equal 2Vy over G, or using Vy from here, we can put it here and find the expression for T1. And the last thing, we have to find what is the time to travel for this ball back to the initial point. Because we have absolutely elastic interaction, we can use here formula for velocities after absolutely elastic collision. That will be this expression, small m minus big M over small m plus big M multiplied by V0. From this formula we can find that if small m greater than big M, this velocity will be positive and ball will never reach initial point. So it means that small m must be less than big M to count this time. So first we can count what is the distance covered by block during time t1. So this distance s will be Vx multiplied by t1, which is this expression, and after all this expression. Now we have to find what is time to cover this distance for the ball to make it an initial point. That will be t2 equal s over v small x, which is this one. And we have to take a positive value. That will be this expression, and total time will be t equal t1 plus t2, which is this one plus this one, and finally when we use beta, which is equal big M over small m greater than 1, we have this formula for total time. That's the answer for question A. Question B. Now we have a motion with friction, and main thing here is that when ball enters this block, it's not rotating. It means that we have kinematic friction between ball and the block, and this ball starts to decrease due to friction too, and also it starts to rotate due to friction. And finally, when this ball leaves the block, it rolls without friction, and this is important point. We can use it. So during the motion inside of this block, we have a change of linear momentum and a change of angular momentum for block. And there are equations. Change of linear momentum, delta P, that's equal force multiplied by delta T, and the change of angular momentum equal force multiplied by radius multiplied by delta T. Or we can rewrite it in form of, we have these two formulas, and here we have force of friction, which is not constant, but still we can do integral for both of them. Basically, as a result, we have the same integral for both equations, and we can just equalize both left parts. So we have delta V equal 2 over 5 r omega. Now let's check what do they mean, these variables. Because finally this ball rolling without slipping, we can write that r omega equal a new vertical velocity, which is we call Vy prime, and delta V, that's a change of velocity due to friction, which is Vy without friction minus Vy with the friction. Now we can put these expressions to our equation and find what is a Vy prime. So we have this equation to find what is a Vy prime, and Vy prime equal 5 over 7 Vy, which is this expression. And finally we can find what is total height. Total height will be V1 prime square over 2g, or using this answer, that will be answer for question B. US Physics Olympiad, year 2014, USA PHO. Final exam. Problem B2. In parts A and B of this problem, assume that velocities v are much less than the speed of light c, and therefore ignore a relativistic contraction of length or time dilation. Part A. An infinite uniform sheet has a surface charge density sigma and has infinitesimal thickness. The sheet lies in the xy plane. Question 1. Assuming the sheet is at rest, determine the electric field E, magnitude and direction above and below the sheet. Question 2. Assuming the sheet is moving with the velocity v in the direction x parallel to sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 3. Assuming the sheet is moving with velocity v in x direction, determine the magnetic field B, magnitude and direction above and below the sheet. Question 4. Assuming the sheet is moving with velocity v in z direction perpendicular to the sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 5. Assuming the sheet is moving with velocity v in z direction, determine the magnetic field B, magnitude and direction above and below the sheet. Part B. In a certain region there exists only the electric field E in form of Ex plus Ey plus Ez and no magnetic field, as measured by an observer at rest. The electric and magnetic fields E' and B', as measured by observers in motion, can be determined entirely from the local value of E, regardless of the charge configuration that may have produced it. Question 1. What would be the observer electric field E as measured by an observer moving with velocity v in direction z? Question 2. What would be the observed magnetic field B as measured by an observer moving with the velocity v in direction z? Part C. An infinitely long wire on the z-axis is composed of positive charges with a linear charge density lambda, which are at rest, and negative charges with the linear charge density negative lambda, moving with the speed v in the z direction. Question 1. Determine the electric field E, magnitude and direction at points outside the wire. Question 2. Determine the magnetic field B, magnitude and direction at points outside the wire. Question 3. Now consider an observer moving with the speed v parallel to the z-axis, so that the negative charges appear to be at rest. There is a symmetry between the electric and magnetic fields, such that the variation to your answer to part B can be applied to the magnetic field in this part. You will need to change the multiplicative constant to something dimensionally correct and reverse the sign. Use this fact to find and describe the electric field measured by the moving observer, and comment on your result. Some familiarity with the special relativity can help you verify the direction of your result, but is not necessary to obtain the correct answer. Solutions. Question 1. Assuming the sheet is at rest, determine the electric field E above and below the sheet. Solution. Due to symmetry, this electric field must go out of sheet from both sides, and using Gauss cylinder, we can make the equation. If cylinder has a base area A, we have this equation that 2E multiplied by area equal to charge inside of this cylinder, which is sigma A over epsilon 0. And from here we have magnitude for electric field is sigma over 2 epsilon. And direction, we have a positive direction in above the sheet in z direction, and negative below the sheet, like here. Question 2. The motion is not affecting electric field. It means that the answer will be the same as for question 1. Question 3. Assuming the sheet is moving with the velocity v in x direction, determine the magnetic field B above and below the sheet. Solution. Assuming that V greater than 0, the right-hand rule indicates there is a magnetic field in the negative y direction for Z greater than 0 and in positive y direction for Z less than 0. From Ampere's law applied to a loop of length L normal to x direction, we have this equation to determine what is a magnetic field B. To get the right-hand rule, note that in time t, an area VTL moves through the loop, so a charge sigma VTL moves through. Then the current through the loop is sigma VL. Applying symmetry, we have this solution for magnetic field. Question 4. Assuming the sheet is moving with velocity v in z direction, determine the electric field E above and below the sheet. Again, the motion does not affect the electric field, so the answer is the same as that for question 1. Question 5. Solution. Applying Ampere's law and symmetry, there is no magnetic field above and below the sheet. Interestingly, there is no magnetic field at the sheet either. Consider an Ampere loop of area A in the xy plane as the sheet passes through. The loop experienced a current of form this one. But the loop also experienced an oppositely directed change in flux of the form this one. So the right-hand side of Ampere's law, including the displacement current term, remains the 0. Question 1. What would be the observed electric field E as measured by an observer moving with the velocity v in z direction? Solution. In part A, we showed that if the electric field was produced by a sheet of charge, then it was unaffected by the motion of an observer. Thus, in general, E prime equal E. Question 2. What would be the observed magnetic field B as measured by an observer moving with the velocity v in z direction? Solution. No magnetic field was created by the motion of the sheet of charge in the direction of the electric field. So the magnetic field in the frame of reference of the moving observer should likewise not depend on the component of the electric field in the direction of motion. When the sheet of charge was moving in the positive x direction, a magnetic field was created in the negative y direction. The observer moving in the positive x direction is equivalent to the sheet of a charge moving in the negative x direction, creating a magnetic field in the positive y direction. That is, an electric field is in the z direction causes an observer moving in the x direction to observe a magnetic field in the y equal z cross product with x direction. Furthermore, the magnitudes of the fields satisfy equation B equal mu 0 epsilon 0 V E, or we can replace mu 0 epsilon 0 with a 1 over c square. That will be this expression. Combining this with the previous equation, we have B prime equal negative 1 over c square multiplied by cross product V and E, which is this expression. Part C. An infinitely long wire on the z-axis is composed of positive charge with a linear charge density lambda, which are at rest, and negative charges with a linear charge density negative lambda, moving with the speed v in the z direction. Question 1. Determine the electric field E, magnitude and direction, at the points outside the wire. Solution. The wire as a whole is neutral, so there is no electric field outside the wire. Question 2. Determine the magnetic field B at points outside the wire. Solution. The current in the wire is I equal lambda V. So Ampere's law yields that B equal this expression, mu0 multiplied by lambda V over 2 pi r in the tangential direction. The current is in the negative z direction, so by the right hand rule, the circular B field lines would point clockwise, looking in that direction. Question 3. Now consider an observer moving with the speed v parallel to the z-axis, so that the negative charges appears to be at rest. There is a symmetry between the electric and magnetic fields, such that variation to your answer to part B can be applied to the magnetic field in this part. You will need to change the multiplicative constant to something dimensionally correct and revise the sign. Use this fact to find and describe the electric field measured by the moving observer, and comment on your result. Some familiarity with the special relativity can help you verify the direction of your result, but is not necessary to obtain the correct answer. Solution. The result of part B was B prime equal negative 1 over c square multiplied by cross product V and the electric field E. Exchanging the electric and magnetic fields, reserving the sign and fixing the dimensions, we have electric field E prime equal cross product V and magnetic field B. Taking the cross product yields an electric field vector that points outward with the magnitude lambda over 2 pi epsilon 0 r multiplied by v square over c square.